Thanks. This work was done with Alex, who is now moved to University of Grenoble, France, out in France. It was done in the FIT lab at Swansea University. Alex has a very nice talk about modular devices called Pixels at 11 o'clock tomorrow. So coming back to Pulp Fiction, what we have done is we looked at a different portion of the body for haptic feedback, that is the periphery of the finger pad. So we are used to having haptic feedback the pad of the finger, but we are looking at the periphery of the finger. So if I may ask you, could you hold your mobile phone in your hand? So you hold it and then imagine it's vibrating. It's vibrating to give you different haptic notifications. So do you really use different pattern of vibration for your applications, for example, long or short vibrations for your WhatsApp message, or different vibration patterns for your applications? Do you really, how many of you use, can I have a raise of hands? Oh, a few of them, that's good. So to have a motivating example, imagine this scenario when you are using a phone, you have a phone in your hand, and then you're using your thumb to have a subtextual conversation. So when you're having this conversation, you're immersed in it, a ball comes at the back of your device, rolls to your fingertip, and then it rolls from the left side of your fingertip to the top and to the right hand side. And when it does it, it actually gives you the progress of your journey if you are in the train. Not only that, it pokes you at different locations to tell you the different stops, frequently used stops. And then when your final stop is approaching, it vibrates and pokes you harder at the fingertip to tell you that, oh, you need to get off, stop your chatting and get off the train. Will this be something interesting and not available in the current devices? I hope yes. Okay. So that's our motivation, and that's our scenario that we thought we continue. So recently they're having lots of work. So these are two works from recent archives where we are instrumenting the finger to give different kind of haptic feedback. For example, the top one, it gives some rotational and translation ones, and the bottom one gives you pseudo transition and normal forces. But what you really want to do is not instrument the finger, but use our natural grips and use the periphery of the finger for some kind of notifications or haptic feedback. So that's our goal. So the main contribution of the paper is look at the periphery of the finger pad. So this is something that has not been explored before. And then we also give a prototype that could be used for haptic feedback at the periphery of the finger. Then we give a control study, human factor study in the paper to and a design space for this kind of feedback system, and also we give you some guidelines for having peripheral finger pad haptic feedback systems. Those are the main contributions of the paper. So looking at some related work from obviously there are a lot of work. This is from the recent guide where a DC motor is used along with a small tacton to drag a tacton along the base of the index finger. And in another one, they used many magnetic shafts along the base of the index finger to poke the finger at different locations. So these are related because we also look at similar scenarios where we take the ball and rub and poke against the finger pad at different locations, and we give similar results. Regarding the prototype, the recent work is SIFT-IO from CHI 2017. Look at how the magnetic disc is sliding on the side of the finger. side of the mobile case. So when you hold the mobile case, it comes and bumps your hand and gives you some kind of haptic notification. Another related work is from us from last year, Kai, where we used liquid metal droplets. So liquid metal droplet is actually vibrating and moving towards the fingertip to give a different kind of haptic notifications. Another related work related to our prototype is Ian Bradley watch. It's a haptic watch where there are two ferromagnetic ball bearings along with a magnetic stage driving them to give you the time in minutes and hour hand, like the minute hand here and hour hand here. So we based our prototype similar to this. We actually didn't know about this, but it's quite related to how we did it. So coming to Paul friction, the overview of the system is it's a back of device system. So what we have is we have small tractors. It could be ball bearing. It could be anything that could come and poke the finger from different angles. And then it could also rub the finger in different patterns, again on the side of the finger. In addition to that, we could also vibrate the tractor, and we can add the vibration to both poke and vibration and pattern and vibration. At the same time, we can also move the tractor along the finger with different speeds for both poking and rubbing, and also with different sizes for both poking and rubbing. Not only that, one can imagine different kind of patterns like having a texture or having a thermal or some heat or other features, or soft, hardness, or other things that you can use. The tacton could be as long as it comes and pokes the side of the finger or rubs the side of the fingers. So in the paper, we have only looked at the mentioned scenarios, and we give a user study to understand the ability to recognize the distinct stimuli around the finger pad, and also we give you some spatio-temporal patterns for haptic feedback. Okay. So this is our prototype. So we used small DVD drive motors, and they're just dragging a stage inside the case, and there are neodymium magnetic disc. So as the stage moves under the finger, it drags a ball bearing. It's not a magnetic ball bearing, it's a ferromagnetic one, so that's why it rolls along the finger. And we had for the test, user test, we had a 3D printed guide and also engraving on the acrylic so that the finger is placed at a consistent location. So there are more evaluations in the paper. I give you one evaluation where we looked at like how fast we can move the we can move the ball bearing. So we tested two speeds, 10 millimeter second and 20 millimeter second, and we saw that the ball bearing is moves very stably, and the noise was only 0.26 millimeters. We looked at different sizes ranging from 3 millimeters to 13 millimeters. So coming back to the experiments, we recruited 16 participants with different age range, with 6 females, mostly right-handed, and only one computer science with very less experience. Like all of them had very less experience with haptic systems. Okay, so for during the experiment, we deployed the prototype upside down for the back of the device scenario. We asked the users to raise their arm on an armrest, elbow on an armrest, so that we avoid the gorilla arm effect. We had a camera below to monitor the movements of the ball bearing, and then we had made one UI for the users to input the values left hand easily. So I won't go into this more in the paper. So for the analysis, for the test, we basically did 2 tests. One is the angle, is for poking from different angles, and pattern is for rubbing the finger with different patterns. For first test, we looked at different types of stimuli. and then also we looked at where the stimuli was felt. For the pattern, we looked at different speeds and size, the effect of them, and also we looked at the strength and comfort for all stimuli. So for the angle, we looked at the possibility of how many different angles one can recognize. So we saw in our test we saw that there was a linear trend for different angles, but obviously due to the human factors they overlap, and it was not clear how many regions one could really use in a useful manner. So we did some studies. So we had 3 separate tests for all the different modes, and we found that we have distinct regions to sense poke, vibration, and poke vibration. I'll come back to it later, but notice that here we can have like 1, 2, 3, and 4 regions, non-overlapping regions for poking. For vibration, similarly, we can have 1, 2, 3, 4 non-overlapping regions for vibration, and similarly here also 4 regions for vibration. So though around the finger periphery, we might think there might be higher granularity. We only have 4 regions, but we can design to have a more, if you like. Okay. For patterns, we had again looked at different patterns, but for the study we decided to do 5. One was going up and rubbing up and down on the left hand side and on the right hand side and on the top of the finger, and then another having a clockwise rubbing and another counterclockwise rubbing. So 5 patterns, and we found that the overall recognition rate was 92.4%. So if you look at the confusion matrix, we can see that it's a bit low on the clockwise and counterclockwise patterns, and also a bit low at the tip of the finger. What we saw that actually few participants consistently confused between the clockwise and counterclockwise. It might be because of the back of the device scenario or how they imagined. I'll come back to it later. And also we noticed that the tip of the finger was actually less sensitive, and it's well known that the inside of the finger is higher sensitive, and that's why we have higher results here. So analyzing the effect of size and speed in using such as haptic feedback system, we saw that we looked at error in size. So the participants told us the error in the actual diameter of the ball they sensed, and speed recognition where they actually recognize the fast speed or a low speed or the zero if they made a mistake. So we saw that there was no significant effect of patterns on this size. So what we mean is could usually employ any size and any speed in the range we use, and it will work. It's very consistent. It's not very sensitive to that. We saw that average size was 2.1 millimeter. So possibly one could use small and large balls also. For the strength and comfort, we saw that there was no significant effect of pattern and angle on strength and comfort, and the only significant effect was of the size of the ball. So basically, for different stimuli, people feel the similar strength and similar comfort. So it's quite good news. So for the guidelines, note that the only significant effect was size. So for the guidelines, what we have like few guidelines in the paper. I'll give you some examples here. As we saw before, there are 4 unconnected regions on the tip of on the periphery of your finger that one could use for reliable haptic feedback. If you poke, you can have 5 points where you can poke. For example, this is just an example, but you can design your own locations. And for vibrations, one could use 4 points for vibration. So again, we saw that vibration felt more spread, which is natural compared to the poke. And also we noticed that away from the fingertip, the haptic resolution was low. It was a bit better for the finger on the inside of the finger than on the outer side. So there are more guidelines there. For pattern, we saw that we when we accounted for the confusion by the participants between clockwise and counterclockwise, the recognition rate actually went up to 98.4%. So it's quite good in. So the overall recognition went up to 98.4%. So participants can actually recognize all the patterns with a lot of confidence. So in the interview, we asked them for different patterns. We test 5, but we asked them for different patterns if they could recognize, for example, unidirectional motion instead of going up and down on the left hand of the finger. If they would be able to recognize only upward movement or downward movement, and they said they will be pretty confident to do that. So there is more space for designing more patterns. And from further test, we found out that it might be possible to use balls of more than 5 millimeter diameter apart to have different sizes, so participants could be able to recognize them, and also speed greater than 10 millimeter second apart could be used to recognize speed. Okay, so from strength we saw that vibration gave a stronger stimuli. A bigger ball gave stronger force stimuli, for example for poking, and smaller ball gave us stronger vibration stimuli. For comfort, there was no preference apart from size, but we noticed that if for smaller ball, they felt stronger, so one could use, for example, a smaller ball for a critical notification. Okay, so that's the study for using the periphery of the finger pad for haptic feedback, and we thought about use case scenarios, and also we worked with the participants, and many of them suggested these. So one was a eyes-free compass. So one could use the direction and the proximity information, direction as in poking, and proximity as in the motivating example going from one side of the finger to the other to give you some eyes-free compass applications. This could be obviously used to avoid distraction because you won't be looking at the screen, and for example it could be used for in-pocket and safe use also. And then for discrete notifications, because now the entire mobile phone is not vibrating, you are getting localized haptic feedback, so it's disambiguous and it could be used for discrete notifications. And one could also have accessible features using this, not only because of it offers tactile feedback or haptic feedback on the mobile phone, but also now you channel some of the notifications to the tactile feedback, so you save on screen space. So it offers you some accessible features. So in conclusion, I hope I have convinced you that using the periphery of the finger pad is a good idea for haptic feedback, and it's a new modality. And hopefully the prototype could be developed to be used to be deployed on a mobile phone. And we gave you design space and found out that there are 5 peripheral zones where poking and vibration could be used. And there are more, obviously there are more information in the paper. I encourage you to read the paper, and thank you for your attention.
We have a few minutes for questions, so if you have any questions, please come up and speak to them.
Hi. Hey, no, that's all right.
You can.
Okay. I was wondering, how did you get the the outline of the hands, like, did you capture it or did you hard code like everything whenever people had their hands in? And basically, I was wondering if you had some kind of feedback within the ball so that it actually knows, I don't know, like the tangent of the finger so that you can actually follow it or something. I don't know. Yeah, so that was my question.
That's a very good question. I forgot to mention that. So in the user study, we kind of so for each participant, we measured the width, thickness, and length of the finger, the proximal, distal, the top third of the finger, and then we mapped it to have the parameters set for each user so that it's consistent. For example, the ball that we used always touches the point which is farthest, the width of the. So we wanted to be consistent that way by measuring the fingers of each user, and because it's a magnetic system, and so there is some leeway, even if it need not be very accurate. So as long as it's bit inside, it always pulls the ball towards the center, so it automatically ensures that there is contact with the finger by making the trajectory bit inside the finger. So,
but if you were to use the ball like at the back of the phone, like how would you like? I mean, everyone's holding the phone like kind of differently.
Yeah. So obviously that's a future work because so in this paper we wanted to know that is it possible to use the periphery of the finger, and if possible, like what are the possible cases, reliable cases. So that was the thing. But now what we're trying to do is actually develop a system at the back of the phone, have some kind of sensing, finger sensing, and automatically do like what you want.
Yeah.
So that's the ongoing work.
Okay, thanks again to you guys out.